If you were flown from airports in cold weather conditions, particularly where there was active precipitation such as snow or rain, you may have seen airplanes being de-iced. But why is this necessary, and just how significant flight operations in cold weather conditions are? Let's dive into it. In this video, we'll be exploring the significance of operating an aircraft in cold weather conditions. We will specifically delve into three things: what causes icing, its effect on the airframe and the sort of hazards that it poses, and finally, the sort of systems and processes that are in place to mitigate the risks. Let's kick off with a bit of meteorology to understand what constitutes icing conditions. You see, water is a well-known component of atmospheric air. Clear air includes water vapor in variable proportions according to the air temperature. There is a maximum amount of water vapor that a given mass of air can hold, and this is essentially a function of the air temperature. When the maximum allowable vapor content has reached, the air is then said to be saturated, and any amount of water in excess of the saturation conditions will show in the form of water droplets or ice crystals. This is what forms clouds. When saturation occurs, excess water then precipitates in the form of droplets or ice crystals. The icing phenomenon is due to the fact that water does not necessarily turn into ice just at or below 0 degrees. Water at negative Celsius temperature may remain in a liquid state. These are called supercooled water droplets. And supercooled water droplets are actually quite unstable. This means that they can freeze suddenly if they hit an object, especially if the object is at a negative temperature. That is the basic mechanism for aircraft icing, and icing conditions are said to exist on the ground when the outside temperature is at or below 10 degrees Celsius and visible moisture such as fog with visibility of 1.6 kilometers or less, or rain, snow, standing water on the taxiways or runways is present. The definition for icing conditions in flight differs slightly. Now, having looked at the fundamentals of what causes icing, let's see why this is hazardous to flight operations. In flight, icing is a serious hazard as it degrades or destroys an airfoil's or wing's ability to produce lift. The aircraft will stall at a much higher airspeed and lower angle of attack than normal. Very quickly, an aerodynamic stall is a phenomenon in which an aircraft's wings are no longer generating the required amount of lift to sustain flight. If stalled, the aircraft can roll or pitch uncontrollably, leading to a serious in-flight upset situation. Aircraft designers do their best to ensure that airframes have smooth surfaces to ease the surrounding airflow. This rule is applied with special care to the wing leading edge and upper surface because smoothness in these areas produces the best lift force. Any type of ice accretion is an obstacle to smooth airflow, and any obstacle will slow the airflow down and introduce turbulence. This will degrade the lift characteristics of the wing. Now, before we talk about the effects of ice accumulation on an airframe, let's quickly review what the critical surfaces on an aircraft are. These are the leading edges and the upper surfaces of the wings, the vertical and the horizontal stabilizer, all the control surfaces, and the slats and the flaps. Some of the possible effects of ice accretion on the aircraft's critical surfaces include loss of lift, as we alluded to earlier, an increase in aerodynamic drag, which affects the aircraft's performance adversely. Icing on the airframe also increases the weight of the aircraft, which in turn increases its stall speed. And an aircraft's stall speed is directly affected by its weight. The higher an aircraft's weight, the higher its stall speed. Also, icing leads to less efficient flight controls coupled with a loss of engine thrust. It can also cause engine vibrations, and ice accretion can also result in incorrect readings on the instruments such as the airspeed indicator and so on. In this little illustration, we have a clean wing on the left and a contaminated wing on the right. As we can see, the airflow over the clean wing is smooth, which is conducive to normal lift generation. On the right, however, the airflow over the wing is quite disturbed due to ice accretion on the leading edge of the wing, and this is degrading its lift characteristics whilst increasing the aircraft's weight. Now, having talked about some of the hazards icing poses to aircraft, let's see the sort of measures that are in place to mitigate the risks. Aircraft manufacturers use various techniques to counter the risks of ice formation on critical aircraft surfaces and sensors. Large modern airliners commonly employ the use of bleed air, which is hot air extracted from the compressor section of the engines to provide heating for the engine intakes and the wing leading edges. They also use electrical heating systems to heat the cockpit windows and various probes and sensors used for measuring the airspeed, outside air temperature, and so on. It is paramount that the sensors remain clear of ice, as any obstruction of the probes could result in unreliable flight parameters such as the airspeed. Now, this can be extremely hazardous, as it could lead to erroneous data being presented to the pilots and its use by various aircraft systems. All of this could jeopardize the safety of the flight. A well-known accident is that of Air France 447 that crashed into the Atlantic in 2009. The findings from the investigation implied that one of the contributing factors was the icing of the pitot probes, or the airspeed sensors, which resulted in faulty airspeed readings in the cockpit. Icing conditions on the ground can be expected when air temperatures approach or fall below freezing, and when moisture or ice occurs in the form of either precipitation or condensation. Aircraft-related circumstances could also result in ice accretion when humid air at temperatures above freezing comes in contact with the cold structure. So that was an overview of the systems that are on board an aircraft to keep ice from forming. But what happens when an aircraft on the ground is in icing conditions in its pre-flight stages and its surfaces are contaminated with ice, or the risk of icing is present? Obviously, dispatching an aircraft in such a scenario would be very dangerous, as it could lead to handling and control difficulties, performance losses, and possible mechanical damage. This is where the concept of de-icing and anti-icing comes into play. De-icing, as the name suggests, involves removing frost, ice, slush, or snow from the aircraft. Now, this may be accomplished by mechanical methods, maybe pneumatic, or by the use of heated fluids. The fluids are categorized by types. Usually, when it comes to de-icing, the use of heated water or something called type 1 fluid may be used. Anti-ice, on the other hand, involves spraying the aircraft with a special type of fluid, namely type 2 or type 4 type of fluids, that provide protection against ice formation for a certain period of time, referred to as the holdover time. This is a time for which the wings and other critical surfaces that have been treated with the anti-icing fluid will resist the formation of ice. Anti-icing is typically considered in conditions where there is active precipitation, or if it is expected to occur before takeoff. The key difference between de-icing and anti-icing is that de-icing is a reactionary step that entails the removal of ice that's already built up, whereas anti-icing is a proactive step that protects an aircraft's critical surfaces against ice contamination. Remember, the anti-icing fluid has an expiry that's called the holdover time, and pilots need to be mindful of this to ensure that the aircraft will be airborne before the expiry of the holdover time. If not, the aircraft will need to be de-iced and anti-iced again. To quickly recap, aircraft incorporate various systems to protect against the buildup of ice, such as engine and wing anti-ice systems, which employ the use of hot bleed air from the engines. Also, electrical heating systems are used for cockpit windows and sensors on the outside of the aircraft, such as the pitot and temperature probes, water and waste system lines, and drains, and so on. These systems, however, such as the anti-icing system for the wings and engines, are only available when the aircraft engines are running. On the ground, with the engines shut down and in its pre-flight stages, measures such as de-icing and anti-icing are used to ensure that the critical surfaces of the aircraft are free of any contamination before it takes off. Alright, so there we have it. We've explored the effects of cold weather on an aircraft, specifically in the context of ice formation and the various hazards that it poses. Flying in cold weather also affects the true altitude of an aircraft, which may call for altitude corrections to be applied. But that's a subject for another day. You see, there have been numerous accidents in history that have occurred because of the buildup of ice on an airframe. One such accident was that of the US Air Flight 405, which crashed as the aircraft was unable to climb during takeoff. This was chiefly due to the ice contamination on the wings that led to an aerodynamic stall and loss of control shortly after liftoff. As it can be inferred, icing and its effects on an aircraft in flight can be extremely dangerous. I trust that made some sense and it wasn't too difficult to follow. If you have any questions or would like a certain topic related to aviation or flying covered, please put that in the comments below and I shall endeavor to cover that in a future video. Thanks very much for your time and support, and I look forward to seeing you in the next one again very soon. Thanks again, and I wish you a great day.